Hi everyone, and welcome to another episode of Mr. Carlson's Lab. Some time back, I picked up a few HP419A null meters. Very nice meter to have around the lab. It's a meter that measures down into the low microvolts and measures down into the picoamps. So I get the meters onto the bench, open up the tops, look inside, and they're missing some very important parts. In fact, they're missing entire circuit boards. So I imagine these units were probably parts donors for some other meters or something like that. And this is most likely the reason why. So looking through the Hewlett Packard service manual for these meters, they specify that if this particular board fails, they suggest that you don't replace just a single component. If you find a bad one, you should replace the entire board at one time. So Hewlett Packard at one time had entire replacement boards for sale. So I imagine that some other meters were probably faulty. Maybe they looked a little nicer than these ones, and they probably made a couple of really nice meters out of a whole bunch of other ones. So I got the ones that were missing the parts. So what else to do? Now I need to reverse engineer the section and design some circuit boards, because Hewlett Packard didn't give any specs for the components in this one little module, because of course they wanted you to buy an entire replacement circuit board. Now the schematic is in the manual, but there are no component values. So I reverse engineered the section, designed some circuit boards, and they worked very well with some neon bulbs. Very specific neon bulbs, I may add, and I'll explain a lot about that here in just a little bit. So I figured if anybody's going to want to get their Hewlett Packard 419 going, these neon bulbs are pretty picky and the entire circuit is pretty picky to get working. So why not just design a solid state replacement? And that's what I did. So I designed a solid state replacement with a standalone oscillator. There's an IC that mounts right to the back of the photo chopper board. And instead of using neon bulbs, it uses LEDs now, and it works fantastic. I'm going to share all of that with you in this video. So lots of neat stuff coming. So I'll talk a little bit about their photo chopper invention, and I'm pretty sure you'll find this very fascinating. So let's get started. This is the HP 419A. This is one of them that I picked up, and as you can see, they're in pretty nice condition. I'll just click this light off here so you can get a better idea of what the meter looks like. It's mirrored and it uses every bit of that accuracy, which you'll see in a little bit. A surprisingly accurate piece of equipment. So it reads to 1000 volts DC and down to 3 microvolts. And if you want to use this thing to measure current, it measures down to 30 picoamps. And then it goes up to the next scale, which is nanoamps. So very, very sensitive meter. So this is the way I got the thing. It's in pretty nice condition. I think this one is the most modern out of all of them. It has this more modern type of receptacle. The early ones had the HP socket on the back, and I'll show you what that looks like. And those cords are a little bit tougher to find. I debated taking this one out and putting it in the actual meter that I restored. This one here is another one that I'm going to go through when I have some time. So I only did one of these things. And this one here I left so that I could show all of you what I went through. So, very nice condition. Click this light back on. So I'll take you through the experience of what I experienced when I picked these things up. So pick the meter up, I'm like, great, I got one of these meters. And then I removed the screws on the back. I think this one only had one screw to begin with anyways. So there's only two to get the lid off the top here. Just kind of slide it back and it pops out like that. You can see the alignment points on the top. I'll just move this around here, move that over there. So make sure I don't back the chair over the lid. So that's one thing to keep in mind if you ever throw an aluminum lid or something behind your chair, get it out of the way while you're working, and you roll your chair backwards, chances are you're going to have a really bad day. So, don't ask how I know this. Alignment points right here. So in order to align this, the lid needs to be on it, and it's actually a little bit more specific than that, and I'll go through the alignment procedure with you as well. They all come with this little, basically repair list on the top here. So if something goes haywire, they get repaired. Now they all have one line filled out. So I don't know if that was from the factory when the thing was released. So kind of a start. I have no idea. 2 screws to get this off. So of course I picked this thing up. I'm all excited. Remove the lid. Have this thing like so. I'll pull the lid back. just like so, and oh, what's this laying down inside here like so? Well, it's the chopper block. What's the chopper block missing? Well, it's missing the circuit board that fits right into that nice little recess right there. So at this point, I'm looking at this, and at first they got shelved for a while because it's quite a bit of work to design a circuit board, and of course I had to, figure out what Hewlett Packard did and everything, because that data is missing on the schematic, which we'll take a look at here in just a little bit. So, and of course, even at that, there is still a little bit of risk. Are the photocells okay inside? So the photocells are right here. So there's one here, and one here, and these are surprisingly sensitive photocells. When I mean surprisingly sensitive, I'm telling you that just ambient light, you cover it, and it kind of still sees light from areas. So if you're measuring this with an ohm meter, it'll go above 500 megs when it's dark. And then just ambient light will bring it way down. So just ambient light around. So very, very sensitive devices. So if you're trying to, determine whether your photocells are good, that's a really good test. So basically just put your ohm meter across it and darken it right up. Maybe shut the lights off in the room. If it goes above 500 megs, chances are, that's pretty good. And if you just let ambient light in there, it will come down into the megohms. And then of course, if you stick any type of a light in here, a really bright LED will bring it down to about 300 and something ohms. Something like that if you just poke a bright LED in there. So 300 something ohms to above 500 megs is, I guess, a safe area to be making guesses. And I tested multiple ones. I tested this one and the one in the meter that I've already done, which works fantastic. And they're all the same. So all the photocells seem to be fine. So at any rate, so that was the issue. Now, these circuit boards, when they were in here, it was a circuit board, a rubber grommet, and then they're supposed to have a aluminum back, and it has little recesses on it, I guess you could say, or if you're looking this way, extrusions that poke against the circuit board to hold the circuit board tight in this little recessed area. In fact, what I'll do is I'll just zoom on into this a little bit. So you can see this little recessed area in here, and the board fits right in here. Now, there was an aluminum back plate that fit on this, and on that back plate, there's little recesses. Now, of course, these are just laying in here, and those aluminum back plates are missing. So the boards that I remade, you can just bolt this directly to this like so, okay? And the rubber grommet that will fit into this area right here is enough to put enough pressure on the board just to keep it tight in here. And if you want, what I did is I have these small little felt tabs that I put on each side of the mounting screw hole. So there's a little felt tab. You can see the outline of the box here, right? So there's a little felt tab here and a little felt tab here, and that just presses on the corners. That's absolutely fine. And you'll see why with the circuit boards. And again, the circuit boards that I've designed and everything without that aluminum back is just fine. So when you're aligning this thing, another thing is you want the side to be on this. You want to keep this shielded. You want absolutely no light in this. And this top cover needs to be on, and it needs to be shielded. You don't want any kind of light shining in there. Even when I was designing this, you'll notice that on these photocells, you can kind of see how they've got almost like little glass beads that seal the lead running into the photocell. You see a little glass bead right there. Well, the neon lights you can see through these glass beads. Now, with the LEDs that I used, I experimented for a long time to get the brightness the same as, so the photocell sees the brightness the same as the neon bulb, which took quite a bit of resistor swapping on my test boards. And what would end up happening when I first put them in there is I figure, okay, you know what, I want those as bright as possible so I get, the furthest range. So basically, when it's off, it's going to try and climb as fast as it can. Again, these have a little bit of a persistence to them, so they're not incredibly fast. They're a little bit slower. We'll take a look at that on the scope here in just a bit. So I figured, okay, so I want this to go as low in resistance as possible, so I drove it down to about 300-400 ohms with a super bright LED in here. And then when the LED goes off, of course, it tries to climb up to the megohm range. Well, you got to remember that these things are flashing back and forth like this. So a bit of the light can kind of reflect on the wall here and cause a little bit of interference. So there's a very fine balance point here. So I found myself just experimenting with the with the actual LEDs that I put on the new board, and made them in brightness to these photocells about as close as I could to a neon bulb, as to the neon bulbs that actually work very well in here. So some other things to keep in mind. In fact, see my flashlight, my horribly intermittent flashlight. See if you can see that maybe shining through there. No, you can't. Well, no, you really can't. So I'll get a LED and I'll show you what that is here in just a little bit. In fact, when the photo chopper block is together, I'll darken things up and I'll show you what this looks like. You can actually see the red light from the LEDs or the orange light from the neons in these little glass seals right here. Now, again, this needs to be as dark as possible in the alignment procedure or your alignment will go out. And of course, the cover needs to be on, especially if you're going to align this thing down at the 3 microvolt range, because moving your hand close to it will affect that. And moving your hand close to the front of the unit will affect the 3 microvolt range. It's extremely sensitive to align, right? And if you want to look at the increments underneath here, you know, we're dealing with hundreds of nanovolts, right? So if this is going to be 1 microvolt right here, right? So if we're going to go below 1 microvolt, now we're dealing with 500 nanovolts at this point here, you know, 400, 300, 200, 100, and then 0, right? So, you know, the noise of the meter, right, just from random movement and temperature change and everything, we're going to be dealing with a little bit of movement here all the time during the alignment. And when you're dealing with sensitivity like that, you're dealing with some pretty extreme conditions. So this thing needs to be covered. You can't have the thing plugged in. That's the reason it came with these horribly corroded batteries that you see in here. So I replaced this. I designed another battery pack, which I'll show you, which fits on the back of the unit, which holds larger batteries than these. So I used Eneloop batteries, and it's much like the battery pack that I designed for that little tech scope. It sits on the back, and when you put the back on, there's 2 screws in the case that go through the case and into these original mounting holes so that nothing is drilled here, and it just fits on the back of the meter, and that will power this for an incredibly long time. This thing is a real current miser in its operation because it, you know, will run off these, you know, old nickel cadmium batteries, right, that are all corroding. You see how green they are? It's actually started corroding some of the wires and stuff in here. So lots and lots of work just making one of these things go again. So I'm going to zoom on out. You're probably saying, well, why did you spend so much time on this meter? Well, because I can share this with you, right? I know a lot of you probably are owning these meters, and those of you that aren't owning them will probably want one after this video because it's a fantastic meter. And I can share this information with all of you. That's why I spent the time with this. So if you guys get any of these meters, any of you get these meters, you guys can get this thing working and make it work properly again, even without the oscillator over here, which I will touch on in just a little bit. So this is the way I received it, and I wasn't too incredibly happy. So there's also a battery that hides down at the bottom. It's originally was a mercury cell. You can't get mercury cells anymore because of the environmental issues of mercury cells. So the next best thing is a silver oxide button cell. That's what you want to replace those with. I have 2 silver oxide button cells in parallel in mine on the bottom, and they make a pretty stable standard. Once they settle down, I'll explain a little bit more about that as well. And of course, again, these have to be replaced. Now, you can't, if you're going to be measuring down in the 3 microvolt range, that's the reason that they have batteries in here, so that you can unplug the thing so that it will measure down there without, you know, having the meter move all over the place from variations in noise and everything. So that's very important. I've read a lot of people have, you know, are measuring, you know, these low ranges with the line still plugged in. That's the reason that they did this. So if you're going to make any sensitive measurements, you want this to be as quiet as possible. And in order to keep it as quiet as possible, you don't want this thing coupled to an AC line. And that's the reason that you unplug it and use the thing on its batteries. Now, I have a lot of people saying, well, you know, why wouldn't you, Paul, have designed a small circuit for the null circuit so that you can use a regular battery and it regulates it down and does stuff like that? Again, you know, complex and noise. So I don't want to run anything off any power supplies in here to set the null. I want something about as stable as I can make it. And the battery works very well for that. Now, I could design a battery-powered linear supply and put that inside and have it isolated from everything so I can use that for the null set. But, you know, that's just you know, you're going to get a little bit more stability than the batteries. That's about it. So I'm not going to really worry about that. Silver oxide button cells is close to their original intention with that mercury battery in the bottom. So lots of stuff to explain and show you here. This is just kind of a preview of what we're going to run into as I'm explaining all of this here. The boards come out relatively easy, so you can see that in the board they have a hole here. And in order to get the boards out of these things, I'll just move this way and grab a screwdriver from behind me here. And you just put this through here like so and go like that. And they just come out like so. And that allows you to service the board. Now on my board, I've replaced the electrolytic capacitors, and I've left anything that's not an electrolytic capacitor, like these ones right here, solid tantalum type caps. I've left them around. Nothing, they're still hanging around on there. No problems at all. So electrolytic caps should get replaced. I didn't bother replacing these because they're very dependable. And yeah, cleaned the VRs and things like that. They've got these nice color-coded diodes to make things interesting. So, you know, very low current circuit, really nothing to go haywire in here unless this was horribly abused, right? It just fits right in like that. And you can see this little crusty piece of foam that's on here that's really not all that flexible anymore. And that fits on top, and as you tighten the top down, it just presses down on the board. Power supply board in the back is mounted with 4 screws, which you can see there's 3 in this one. So 1, 2, 3, 4, and then all the wires around the side. Now I noticed in the HP service manual that they've got these connections down at the bottom as well as all the other ones. So whether these are a later or earlier version, I really don't know, but these connections here are on the side. And that's something that you'll notice in there. Electrolytic to be replaced, electrolytic to be replaced. Little things like that. Not a whole lot to really go wrong on this thing. Very simple oscillator circuit in here. You know, a frequency adjustment here and current adjustment for the factory neon bulbs, which couple into this portion right here. And then that runs with a cable down over the side and comes out here. So it goes between the sidewall here and this unit. It's a shielded piece of cable, and runs into the chopper block, which is then, of course, bolted to the side. Another thing to keep in mind while it's on my mind is that just say you get one that's like this and it is missing parts and pieces. Say that little aluminum back piece is missing here and somebody's taken the screws and put the screws in. Be very careful because those screws are a measured length, and if you drive a screw too far into this hole, you'll drive it right into the photocell. I don't know if you can see that. What I'll do is I'll zoom right on in, as close as I can get. And if you take a look in there, you can kind of see a little bit of the photocell wall. So you can see a little bit. It looks like somebody may have made contact right in there. See that little bit of red down in there? May have made contact with the photocell wall, and there are the photocells right in there. Fancy little devices right in the bottom, and then there's the ones on the other side as well. So you don't want to damage those, because if you damage those, then you really have a brick. So you want to be very careful with these photocells in here. So I was very careful just to run the screw in through the side and see where it got tight, because they did get tight and they were bottoming on the photocells. So ran them into where they got tight, and then of course somebody had mine out so many times that I put the screw in one more time and it took the threads out. So if anything else could go wrong, right? So I found some shorter screws with kind of a coarse thread on them, and they were the perfect length, and just twist like that, and it holds the thing to the side of the wall nice and tight, and it worked out well. So I'll show you some of those screws as well. They kind of make their own threads, and worked out okay. So as you can see, these things have seen a pretty tough life. I'll just zoom this out here again. So what I'll do is I'll get the schematic and I'll start explaining what's actually going on in this device, and we'll get into how I designed another neon board, and then how I designed the solid state replacement, which I will be using in all my future HPs. So I have 3 of these things. 2 of them will get restored, and I'll just keep the other one for parts or something like that, because it's pretty bad. So at any rate, there we go. We'll grab the schematic and be right back. This main schematic closely resembles my Hewlett Packard 419A null meter. So this really is the majority of what's inside that little null meter. Really, I have to say, there is beauty in the simplicity of this design. For such a simple device, such a simple design, the accuracy that this thing obtains is really quite incredible. And this just goes to show you, the brains and the engineers that put this together, really quite astounding. So hats off to the Hewlett Packard engineers that put this together. You really did a good job. Just look at this. It's a handful of transistors and some other components laid out on a bunch of boards. Lots of thought went into this modulator and demodulator section here with the feedback path and everything like that. Now the board with the neon bulbs and the power supply is on another schematic, and we'll take a look at that here in just a moment. The reason we're going to take a look at this first is because those neon bulbs sit between these photocells right here. So this is that chopper block that was laying on the wiring inside that meter when I opened the lid up. Now you'll see here, first of all, we have DS2, DS2, DS1, and DS1. So DS2 is one neon bulb, and that shines on, you can see the arrows, shines on the photocell. So that's one bulb sitting between two photocells. So that's a bulb in the center and two photocells. So there's a photocell on each side of the neon bulb. And this is in the upper portion of that block. So when we took the lid off of that, the Hewlett Packard meter there and looked inside, the neon bulb that's closest to the top of the lid is DS2. Now, on the bottom portion of that chopper block is DS1. That's another neon bulb, and that's sitting between these two photocells right here. So two photocells on the top, neon bulb in the center, completely isolated from two photocells on the bottom and a neon bulb sitting there. Now, those neon bulbs oscillate in a back and forth pattern like this, and there's quite a bit of dead time between the lighting and I guess you could say light and dark portion of the neon bulb. So, in other words, the neon bulb strikes, so it strikes on, it completely shuts off, there's a bit of dead time, and then the other neon bulb strikes, stays on for a short period of time, shuts off, quite a bit of dead time, and it goes back and forth like that. And you'll see that on the oscilloscope here in just a little bit. And when I was designing the solid state board, I wanted to mimic that action as close as possible to keep the operation of this as close to the way the original engineers designed this. But instead of using those neon bulbs, I'm using LEDs now. So just a quick overview of the way that this thing is working. I don't want to spend too much time explaining this schematic just because we really need to focus on this. And I could spend a lot of time explaining the way that this thing works. And again, this really is quite a beautiful design. AC amplifier, DC amplifier, feedback path, and all that kind of stuff. So first of all, I cut the whole entire first portion with the attenuation network off the schematic, because if I had to get that all into the shot, this schematic would be, this portion of the schematic would be this big, and it'd be very hard to see any detail. So really all it is the banana jacks on the front portion of the meter going through an attenuation network. There's that that null battery in there, the null supply battery is in there as well. Not too important to get the idea of what's going on here, but that little null battery just allows you to null out any offset between, if there's, say you attach a supply to it and the meter goes over because there's a bit of offset, you can use the null to null that out so you get an accurate reading, and that's what that battery, I guess you could say, counteracts. So that's all in the front portion here. So a DC level is present on the two banana jacks. Say we're putting a DC level in there because we want to measure something. So a DC level goes into the front, it goes through the attenuation network, and we have a DC level present here, an attenuated DC level here. This area right here is just to get rid of any superimposed AC on that DC signal, or on that, I should say, DC level at this point here. So if there's any AC on there, if we have a meter that's going to measure down into the microvolts, any AC on that is going to cause that needle to move around, and it's going to cause inaccurate results. We're not going to be able to read it very well, right? So they put a filter on the input here, and that's just to get rid of noise and AC. So we have a DC level present here. Now, if you recall, I mentioned these photocells in complete darkness, they go above 500 megs, so you could look at that like an open connection. And then when the neon bulb strikes between the two photocells, this one here and this one here, the resistance drops quite a bit. And with the brightness of the neon bulbs, that would be in the low K ohms area to maybe, the really bright neon bulb, maybe, to the high hundreds of ohms, okay? So you could look at it as an open connection, above 500 megs, and then it comes down to about, say, a K, just for examples, okay, for an example's sake. So 500 megs to down there. Now keep in mind that the photocells themselves have a bit of a persistence. So when the neon bulb goes out, the resistance of the photocell has to climb. Okay, so there's a bit of a persistence in there. So it may not get to that incredible level with the neon bulb moving on and off that fast, but it is going to go up and down very quickly. We're going to have they want to create a connection that's close to being open, and then of course they're going to want to close that connection when the neon bulb comes on. So high resistance, low resistance, high resistance, low resistance, and that's what's happening with this. And it goes back and forth like this. So this is high resistance, low resistance. This is high resistance, low resistance, high resistance, low resistance, high resistance, low resistance, and it just moves back and forth because the neon bulbs are doing this. Obviously, we're going to get a chopping action, hence the chopper block. Now, you can see that the DC is blocked by this 0.1 microfarad capacitor. So this is an AC amplifier right here, and they have all the specs for the gain of the AC amplifier in their spec sheet if you wanted to actually work that out and check that through the attenuation network and everything like that. The output of the AC amplifier, any DC, is blocked by this 1 microfarad capacitor, and again we have this photocell right here, and this is known as the demodulator. So at the output of the demodulator is a DC level that's proportional to the amplitude of the square wave at this point right here. And then we have a DC amplifier right here, and it goes on to the meter, and we have our feedback path. The feedback path is denoted by the dotted lines right here. So anywhere you see a dotted line like this, we have feedback paths. So it's kind of nice that they've done that all over this schematic to make everything, that much easier to, follow if you're going to be, following the signal if you wanted to find anything. So you can see feedback path here, and so on. So that's all that's really happening here. So the output of the modulator block here, so how can I put this? There's a square wave here, and the amplitude is proportional to the difference between the amplitudes of the DC voltage and the feedback, which is on this path right here, because we have this action happening here. And of course, we have the AC amplifier, which is amplifying we have pulses at this point, right? We're getting amplification here. And then, of course, because we have a feedback path, we're going to have a very accurate closed loop gain, and that's going to give us our very correct readings on our meter here. Again, such a simple design, such a beautiful, simple design to get such accurate results. It really is just goes to show you very, very good engineering. Minimalist design, you could call it that. Nowadays, to do something like this, you'd have ASICs and embedded firmware, and you'd have ICs all over the place. It's just going back to this, such a simple analog design for such a great result. So what I'm going to do is I'll get this out of the way, and we'll take a look at the neon bulb that sits between both of these photocells, and I'll explain what's going on there. This is the power supply, neon driver, and neon subassembly schematic that closely resembles what's in my Hewlett Packard 419A. So in my unit, this entire board was missing, and in their manual, there is no component values for anything on this board. They want you to buy this entire circuit board because they put some time into aging the neon bulbs to make sure that they strike in complete darkness and things like that. So just what's written on the schematic right now, if you're trying to get one of your meters working, what you see here is a lot of information. So first of all, R2 and R1 are 20k ohms, and they're an accurate value, 1% value. CR2 and CR1, I experimented with lots of different diodes, and for example, if you use a 1N4007 or something like that, you'll find that you might not get your neons to fire in complete darkness. Oddly enough, 1N4148s, which have a very low reverse breakdown, same with the BAS16 WTP, which is a surface mount device, worked very well. That, in conjunction with adding this 1000 picofarad capacitor from this point to this point here, makes very reliable striking in complete darkness with many different neon bulbs. Now, don't let that lead you astray. Most neon bulbs that are available nowadays will strike between 65 and 90 volts somewhere. And you'll put them in and you'll get a neat looking little waveform on your scope, but it won't be the proper waveform. So the special, I guess what's special about these neon bulbs is they strike usually above 110 to 112 volts. That's where these ones strike. And they were bright back in the day. So finding neon bulbs nowadays that reliably strike above 112 volts, maybe 120 volts, something like that, is actually getting kind of difficult. I ordered some neon bulbs that were supposed to strike at about 135 volts, and they come in at about 100. Most all of them come in at 100. So lots of neon bulbs I experimented with, and lots of them don't work. In fact, I'll show you some of the neon bulbs I experimented with here in just a while, so something to keep in mind. This capacitor here can be, I find, anywhere from 0.003 to 0.0047. The ones I used on my board I used 4.001, so I ended up with 0.004 in the end, and that worked out very, very well. So my suggestion to you is if you have your neon board and it's not firing reliable and you want to experiment just using replacement neon bulbs, put the capacitor in first, and if you're not sure about your diodes, replace them with 1N4148s because those will fit right onto the board before you start experimenting with the neon bulbs. Because this and the diodes alone really change the game when you're trying to make neon bulbs strike and then strike in complete darkness. Striking in complete darkness is a very important thing, and strong neon bulbs are needed for that. Now, one thing that's not really known about neon bulbs is they have a characteristic that they self-polarize when both of the rods inside are not lit. So say they're operating on DC. Only one rod inside the neon bulb will light and the other one won't light whatsoever. And when they do that, they self-polarize over time. Now, when you're looking at a neon that's normally operating on AC, it looks like both the rods are lit. Well, what's happening is they're actually lighting back and forth like this. This one lights, then this one lights, and it's moving back and forth so fast it looks like both rods are lit in the neon bulb. When you're dealing with DC, a DC pulse, or just DC alone, only one rod will light. And again, the neon bulb will have a tendency to self-polarize. So if you have a bunch of neon bulbs, even if they're new, usually they're aged. So if, say, it doesn't work, say you plug two neon bulbs in and the oscillator isn't working correctly, take the bulb out and just turn the bulb around and try it the other way. I found that a completely not oscillator that won't work, so a board that won't work if I just take the bulb out and put it in the other way, gave me results. So you might want to keep that in mind as well. So whether they're, I guess you say burning them in on AC or whether they're doing it on DC, I really don't know. But even the new bulbs, they'll strike at a lower voltage or a higher voltage when you reverse the bulb. Something to keep in mind. Self-polarization. Very interesting thing that happens with these things. I should mention, before we move on, I've replaced the indicator light on the front of the Hewlett Packard 419A. So it's been changed from a neon bulb to an orange LED. And if you own one of these meters, you're definitely going to want to make this modification for this very reason. And this is the reason right here. You'll notice that we have a plug here, and the line cord plugs into that socket on the rear side of the Hewlett Packard 419A. And that gives power to the primary of T1 right here. And you'll notice that the factory indicator bulb is a neon, and it's across that primary winding. What does that tell us? Well, if we remove the line cord and we run on the battery, so we're relying upon the current from the batteries right now to power the unit up, we have no indicator light. What even makes this more, I guess you could say, confusing is that unless you have the off button pushed in, the unit's on. So just say you have the needle on the unit, very well zeroed. So it's pointing right at the zero and all the buttons are just sitting flush. The unit's on. And it can be left on for days, weeks, however long, because there's no indicator light to tell you that you've left the unit on. I'll show you what I mean here in just a little bit. So in order to get away from that and completely draining the batteries inside, what I did is I put an orange LED in behind the front panel and I just removed this neon bulb. I've saved this neon bulb. We're going to test this out here in just a little bit as well. We're going to see if this works in the oscillator board. If it does, then we have a spare neon bulb right in the indicator lamp. But anyways, we'll get to that in a little bit. So what I've done is I've installed an orange LED right here, and it very closely looks like the color of the factory neon bulb, so it doesn't even look like anything's been changed. Now, the neon bulb only operates when the unit is plugged in, so whenever you're making sensitive measurement, the neon bulb does not light because there is no line cord and there's no power to the primary. The original wires that ran to this neon bulb are just twisted pair, and it's a piece of, or two pieces of yellow wire that run across the front of the unit, around the side, and to the back. Those are those two yellow wires that you'll find in your unit. Now, since this is an LED and this is going to be on even during sensitive measurement, just in case there is any noise present anywhere in the unit, I want to keep this as quiet as possible because this is very close to those jacks in the front of the unit. So I have a 1 microfarad tantalum capacitor across the orange LED, and I'm running shielded cable from the back side of the unit all the way up to where the LED is. So this is the shield. Both the negative 13 volt line and the positive 13 volt line are shielded directly to the lamp, and this 4.7K resistor is right there. Now, it may not need this shielding, it might be just fine, but getting the front panel off this unit is a real pain, and I don't want to go back in there just in case there is noise present. So I'm just going to take no chances and run a piece of shielded cable from the back to the front and not remove that front panel again. So something to keep in mind, orange LED, extremely beneficial over this neon bulb right here. And if we find that this neon bulb actually works in the oscillator circuit, that's even more of an excuse to remove it. So let's move on to testing some of the neon bulbs, and I'll show you how that circuit works now. Some of you are probably asking yourself, how much time do you actually spend with these neon bulbs reverse engineering this circuit? Well, I can tell you that I did put quite a bit of time integrating all sorts of different bulbs and putting them in different categories, like this. So just keep in mind that these were plugged in both ways into a fixture, 2 at a time. And then there were these. Nice little matched pair that I got out of that. And these ones over here as well. Pairs that worked. These ones are actually, they have a marking on them. So this is how they work the best in the circuit. Oh, and then there were these ones too. Quite a bit of time in testing those. And these ones, these are different bulbs again. And these ones. And all of these. And these ones here. And all of these. And those. And I even tested some neon regulators. I'm kind of sick of neon bulbs now. So I did this just so I could share this information with all of you. And then, in the end, I redesigned the board and just made a solid state version. So I'll show you some of those boards now. The result of this. And pretty much never wanting to see a neon bulb ever again. Here's the first batch of neon replacement boards that I created for these HP 419As. So the board started out like this, and I gave myself a lot of room to mount surface mount components on here so I could try different components. As you can see, the pads are very big. The reason these pads are so big in the center here is because the capacitors I'm using are high voltage surface mount types. So the boards start out as that right there. Kind of hard to keep the glare off this, but they start out as this, and then I tin them. And then the boards end up like this with the components. Now, all of these components, these are 10K resistors to make 20K, and each one of these have been graded. So I'll pull a whole bunch of them off the reel, and I'll measure each individual resistor, and when I find 2 of them that are 9.9999K ohms, I'll mount them here. And the same with this side here, so they're very closely matched. These are those surface mount capacitors down there. I made these cables up here. This is actually an HDMI cable that has been, actually no, it's not, it's a USB cable that has been cut, and I just used the wires inside here and color-coded them with some gold connectors on them so that I know where they go on the unit. The blue wire is actually supposed to be a white wire, but I had blue heat shrink and my white heat shrink was too tight, so I just know that the original white wire is a blue wire. You can see the white wire comes out here. It's on this end, it's coated with blue heat shrink. So all of them are the same. They're all the same. Each one of these have been graded, and the neons have been thoroughly tested in the dark, and also to make sure that they, you know, with the maximum amount of current that they keep oscillating, and with the minimum amount of current they keep oscillating, and to make sure everything is good, to make sure the waveform looks nice. And they worked out very, very well. So once I finished designing these, I figured, oh, why not design a solid state version of this? So I put some more time into a solid state version, and we'll take a look at those here quite quick. One of the boards is actually in the meter that we're going to be testing these on. I'll show you that board, and I'll also show you the experimental board that I have, and I'll talk a little bit about it as well. And I'll show you the schematic too. This is the 419A that I have spent quite a bit of time on, and I've used this one to do all my testing as well. This is the battery pack that I've created right here, and this will just fit right onto the back side of the unit, and we'll use the existing mounting holes. So that's what I'll be running this thing on. Just to let you know how much of a current miser this thing is, these Eneloop batteries come charged, and they've been charged. I've done all my experimentation with the original charge on those Eneloop batteries, so who knows how long they've been sitting. And I just put them into a battery pack, put them in here, and the battery voltage has hardly changed throughout all of my experimentation time, and I can't even tell you how many hours I've put into this. Well, you obviously know with all those neons that I just showed you. So plug this in here. Everything is shielded. So the cable itself is shielded from the inside here. There is no loop created, so there's a shield inside this cable that runs right up into here. And then the box itself, obviously, as you can see, connects to this connector right here. So there is no looping happening with any grounds or anything like that. So the battery is connected. So if I turn this on, you can see it has to be pressed in the off position to turn it off. So even just depressing the off switch will turn the thing on. And as you can see, the little orange LED lamp on the front there looks really nice. It's much like the original neon. And if I just let this settle, you can see it just sits right on the 0. I haven't even touched anything in who knows how long now. At least through this entire video. You see it's right on that 0 line. So can you imagine just having all of these buttons out like I explained, and no line light, because this wouldn't light normally with the battery, right? Because of the neon bulb. So you wouldn't know anything. So it would just sit like this, and it would be left on, and it would completely drain the batteries. So that's a real handy thing to have in there. And again, the color is very close to the original neons. Now this is on right now, and this has got the solid state chopper block, or the oscillator board in the chopper block here. So what I'll do is I will turn off a bunch of these lights, and I'll see if I can show you the light shining through those little glass beads on the photocells. See that? See that in there? So those are the LEDs inside this photo chopper block. Now, here's the thing. I tried red LEDs, green LEDs, blue LEDs, ultraviolet LEDs, all sorts of different colored, the original orange LEDs, just like this one right here. And the color that worked the best with the photocells in this block are these red LEDs. The color red works fantastic. So basically what I'm trying to say is when I light up the block with a red LED, I can bring it, down into the low, ohms. Whereas if I was to do the same thing with an orange LED, I might be maybe 3 or 4K above, even with the same brightness. So it's sensitive to these orange or these red LEDs. The orange LEDs, it didn't have as much sensitivity. Green ones were horrible. Blue didn't work very well. Even my ultraviolet LEDs didn't work very well. But red, it's very sensitive to red. So the red LEDs were the choice. If it worked better with green LEDs, they would be glowing green right now, right? So quite a bit of time. You can even see the photocells on this side. So the little glass beads where the lead-in wires are sealed to on the photocells, right in there. I have the newly designed neon board in my drill vise right here, and it's plugged into the same area that the factory neon board would plug into on this HP board. So there are 4 pins right here, and the factory board plugged into these 4 pins. So I designed up these little cables using that USB cable I talked about earlier, and a bunch of little gold connectors I had, and put some heat shrink over the top of them to heat shrink them tight, so that when I actually plug the connector onto the pin, the heat shrink that's on the outside keeps a lot of tension on that connector, so it worked very well with the actual tension of the connector alone. Can't tell you how many times I've removed this board. This is the actual board that I did the experimentation with. This has been out of here many, many times, and the connectors are still very, very tight. So that worked out very well with that little piece of cable, and everyone had the same cable on it. Now, this board here operates with the oscillator on this factory Hewlett Packard board. The one that's installed in the chopper block right now is the new solid state version, and it runs completely independent of anything in this Hewlett Packard meter. So it has its own oscillator, and everything is, I guess you could say, fixed. There are no adjustments. It's basically plug and play. You just put the thing inside there, connect it to the battery terminals, and as soon as you turn the switch on, it works, and that's all. So there's no current settings, there's no frequency settings, no anything like that. Everything is just fixed, so it's very nice. So since this runs standalone, I can leave that solid state board in the chopper block, and I can run this one at the same time. They won't interfere with each other, they don't see each other or anything like that, which is kind of nice, so I can leave this alone. Now mind you, later on I'll remove this from the wall and I'll show you how that new board goes in there, and I'll show you the LEDs that are on it and what I've done to the LEDs, all that kind of stuff to make everything work just right. So actually there was quite a bit of prep to the LED. Very simple prep, but there was prep. So when I was designing this board here, I didn't want to electrically couple into the neon bulbs to look at the signals directly, because this is so incredibly sensitive. Even connecting an oscilloscope probe to this oscillator board could cause issues. Not only that, if I'm clipping a scope on here, I can't completely cover the neon bulb, and if I can't cover it, a very interesting effect with these neon bulbs is, even in complete darkness, if they're both flashing, the flash of this neon will help this one work if it's weak, because there's light there. So, for example, if I cover one of the neon bulbs, the other one might start flickering and acting erratic. That's how sensitive this is. So, since I didn't want to electrically couple into this, I designed an optical sensor and fit it inside this BNC connector right here. So this just clips onto here and goes directly into my oscilloscope. I've tucked a piece of heat shrink tubing in here, which allows me to couple directly into the neon bulb like so, and I can completely cover it so it goes into complete darkness and I can watch it. And it's the same with this one right here, and it also allows me to look at the actual flicker and see what the photocells in here are actually seeing from this neon bulb. Now keep in mind, the neon bulbs that go inside here are, set to a certain brightness because of the current, right? Obviously, if you increase the current, they will get brighter and consequently probably burn out faster as well. But if you load the photocells in this block, you put any type of current across them, if it's got a square wave output, the more current you put across it's going to try and shift that and change it more to looking like a sawtooth. So keeping light current on the photocells is a very important thing. So when I was testing the brightness to get an idea of where the brightness was of these LED, or of the neon bulb, so I could compare it to the LED board, I loaded the photocells, and by changing the loading I could also change the waveform a little bit, just because, of course you're putting current across that very, very sensitive device. So when I was setting the brightness of the LED board, I put this one in the chopper block in the unit that I'm actually using for parts right now. I put this in the chopper block, and I would load the photocell and look at measurements on the oscilloscope screen and compare what I see with the neon bulbs in there to what I see with the LEDs, and that would help me, I guess you could say, adjust the brightness of the LEDs until I get the exact same amplitude and waveform out of both boards. When I achieved that, I know I had the same brightness with the LEDs that I have with the original neon bulbs. So there's quite a bit of experimentation there as well. So that all worked out very well. So at any rate, back to this. So my scope is tied into this right now, and I'm going to show you what the correct waveform looks like, and I'll show you what this looks like when it's lit up. So again, this adjusts the current, this adjusts the frequency. This was adjusted a long, long time ago. I imagine it's probably still an adjustment. The factory manual calls between 140 to 160 millivolts on the oscilloscope screen to the larger pulse, and I'll explain that here in a moment. And of course, they're measuring that across a bunch of 51 ohm resistors. Those are the shunts that you're measuring the voltage across. So what I'll do is I'll turn on the board, and that's what the neon bulbs look like when they're lit. You'll notice that only one rod in the neon bulb is lit, so I'll zoom on into that just a little bit and take a closer look. Pardon the movement of the camera. So you can see one portion of the bulb isn't lit, and of course the other rod is. So one rod is dark, one rod is light, and of course that's going to create that self-polarization effect inside this neon bulb. Not so incredibly important because I don't plan on taking the bulbs out and changing them around, but I am going to remove these bulbs, and I'm going to put sockets on this board, and I'm going to show you what other neons do and what kind of a waveform that you'll get out of neons that don't work correctly. And we can also test the neon that I've removed from the indicator lamp and the one that out of the other unit to see if they'll actually work in the circuit. That'll be kind of interesting to see. They are kind of darkened, so they do have some time on them, but it'd be kind of interesting to see. So I'll take a look at the oscilloscope screen here, back this out, and I'll bring you over to the scope screen. Again, pardon the camera movements and all that kind of stuff, heavy camera. So right now, I have the cursors on, and you can see the delta is 150 millivolts between the two cursors, and that's a very comfortable, I guess you could say, center value between 140 and 160, so I have it set at 150. If I move the current around, I'll just move the current VR around, I'll bring it down, I can bring current up, and as you can see, it changes the amplitude of the waveform there. And of course, we're using the larger waveform to set the current. Now, these neon bulbs work exceptionally well in this circuit. Some neon bulbs, if you back the current down too much, it'll come into oscillation, look perfect, but as soon as you bring the current up, it just goes all funny. So it doesn't operate properly. So these neon bulbs here seem to be, I guess you could say, the best out of the entire lot, and I used all of those ones to create these boards. One thing I did notice about the orange color of these neon bulbs. So the orange color, they are a very orange to red colored neon. I've noticed that a lot of the modern neon bulbs, they have kind of a powdery orange color, kind of a very soft, almost like a creamsicle color orange to them, where this is much more red. So I think these are considered an ultra bright version. So maybe they've used a, pure gas in here, maybe less of a mix or something like that. But they are a very, very bright neon bulb. So something to keep in mind. Now again, the neon bulbs, as long as they strike above about 110, 112 volts, something like, chances are they're going to work in this circuit. So just make sure that your bulbs strike at that level. And you can do that with just a variable power supply and an actual current limiting resistor. Basically bring your variable power supply up until it strikes, and then measure the voltage of the strike when it actually comes into action. So when the thing actually lights up. So neon bulbs are kind of interesting. So they look like an open circuit until they strike, and then when they strike, they really, if they're on AC, they become a low impedance device, right? So interesting kind of bulb. So that's why we get the waveform that we're getting here, especially with that little tail on the top there. So I'll just bring you to the screen right here and move this out just a hair. So now you can see at the bottom of the screen here, you can see that there's a duty cycle with the blue trace. All right, so that's my optical probe. Now the big trick in designing a solid state board for this is I have to look at each individual pulse, because right now this is combining both pulses on this upper signal here. I'm hearing something in the background move around here. I'm wondering what that is. Anyways, on this upper signal here, on the upper waveform here, you can see that the frequency for this is 324 hertz, around there in that area. It's moving around a little bit because, you got that overshoot that's kind of moving up and down on this end right here. So because both of the pulses are contained within this one line here, we see the combined frequency. Now, the interesting thing about this whole deal is that this is one neon bulb, and this is the other neon bulb, and I can show you that by just pointing my little optical sensor close to one of the neon bulbs. Let's turn this around here, like so, and get that as close to it as I can, right about there. So you can see that that pulse right now, this is the upper neon bulb, it's corresponding to the small pulse. It's right below it, so it's in sync with that pulse, you could say. Now what I'm going to do is move this over to the other one, and you can see that the pulse is corresponding to the larger pulse. That's the lower neon bulb. Now something that's very important to take a look at is take a look at the duty cycle written in blue on the side over here. So the positive duty cycle is about, we can say, 25%, and the negative duty cycle on the bottom is about 75%. Okay, so that makes sense, right? Now, if you look at the frequency just above all of that, it says 161 hertz, and you can see, it's going to be roughly half of the total here, right? So it's going to be half of the total frequency because we're missing one pulse here. We're only looking at the big pulse. Now, when I'm designing the solid state board, I need to design a board with a lot of dead time between one pulse. And then the other pulse will have to have the same amount of dead time. It's just that that pulse will have to appear right in the center. So basically, I'm creating two pulses, and I need these other pulses to sit right here in order to create this. And that really is the trick designing a solid state board here. So if you remember, positive duty cycle 25% and negative 75%. When we take a look at the solid state board, you'll see that. Let's test out some random neon bulbs in this now test fixture. So this is the same board with those other two neon bulbs removed, and I just put two sockets on each side here, and I can plug random neons in. Now this thing is on right now, so there's high voltage present on there. Very low current high voltage, but I don't suggest that you do this at home. Leave the dangerous stuff to me. So when I say low current, it's very low current. Okay, so here's just two random bulbs that I picked out of a bag here. I'll just plug them in. This is like threading a needle from this distance right here. Okay, so you can see we have a waveform there. Now, if you look, they're very close together. Technically, if I had two bulbs in here, it would look like it's actually working correctly because they're so close, right? Put this one in. Look at that. Now, that doesn't look good, so what I'll do is I'll adjust the current here just a little bit. You can see it's just not working. Now, if I was to lower the current to this, I imagine I'd probably be able to get these bulbs going. So this one here looks nice and strong, and this one doesn't look as well lit. So what I'll do is I'll just, I'll try another one here, see what happens. So I'll get rid of this one. And as you can see, kind of cleans up, a little higher amplitude. So I'll just plug this one into the test fixture here. And we get the same kind of effect. Well, actually, when I touch it is when that happens. So it might be because of the dark. So I'll just take a piece of heat shrink tubing and slip it over it and see what happens. It's more of my hand close to it that's affecting this bulb. You can see how sensitive this circuit is and why I wouldn't want to tie into it with an oscilloscope probe. Just bringing my hands close to it is affecting this, right? So, piece of heat shrink tube pulled that out. So I'll just try another one. Try another neon bulb. Down there. Move this over into here. Same kind of effect. So let's get rid of this one. And try this one here. And as you can see, we've tested a whole bunch of neon bulbs, and this is the same kind of effect that we get. So I'll play with the current here just a little bit. Make sure that screwdriver pops in. There we go, into there. And as you can see, no good. So I'll get rid of these ones. Put them down here. And I'll just randomly try some of the ones out of this bin. And I'll show you. I'll just plug this one in. Just any old random neon. Not bad looking. Let's see one that has decent sized leads on it. That one has decent sized leads. That should fit down into there. Now, if you were to look at this and you put two neon bulbs in, they look like they're lighting really nice, right? Everything looks very good with these two neon bulbs. So now, the amplitude is the same, But as you can see, the spacing is very deceiving. So if I put this to here, you can see that this bulb is pulsing the same as the entire upper chain. So you can see that. And if we go over to this one, it's the same thing. So they're both pulsing at the same time. And they're pulsing at the right frequency too. So you could see how this could get very confusing if you don't know what you're looking for. Again, we need that staggered pattern in order for this to be oscillating correctly. When it's staggered is when they're pulsing at about 160 hertz or something like that, right? Get rid of this and get rid of this one. So I'll take some of these ones that I found that seem to work okay. Now these are the ones that I put back in the bin for some odd reason. I think they were too picky. So these are some of the... You see how bright that is, right? Kind of odd, and I'll plug this one in here. Seemed like moving my hand close to it. Look at that. We have the correct waveform here. There's no problems with that, right? You'd think that's okay. Now, what happens if I cover one of these up? So I bring it into darkness, okay? So I don't know if I shut the light off here, okay? Make it nice and dark. I'm going to slip a piece of heat shrink tubing over one of these neons. Look at that. It doesn't like to fire in complete darkness. Right? This is kind of tight. I think it's going to remove that neon. It is. So I'll put it back in there again. Nothing like threading a needle in the dark. So there we go. So you can see right now it looks like it's operating correctly, but I think this heat shrink tubing here is just a little bit larger. Hopefully it won't pull the bulb out this time. So I'll just slip it over top. Look at that. And that's the problem. This one doesn't like the dark. See if this one likes the dark. This one doesn't care. See, this one's okay. But this one is afraid of the dark. So, we know that there is a problem there. So let's replace this one with, say, another one. Take that one out. And this one I've marked as noisy. So, actually printed noisy right on the bulb. And there's the noise in that neon. So we definitely wouldn't want that in the circuit. And if we take a look at that with the optical sensor, you can actually see the noise in the optical sensor at the top here. I'm just holding this. It's very sensitive. Try and keep that as steady as possible. Right? And this one here is just nice and quiet, right? You see the rigid edge on the top portion there? Now, I'll up the current of this one. So I'll turn the current up and see what happens. Because the current is a little bit low. Look at that. It cleans up. So far, so good, right? We're thinking this is all pretty good. Let's see if this one here likes the dark. Look at that. It doesn't like the dark either. Now you can get an idea of why Hewlett Packard wanted to sell you just a board with neons that would be happy. So this one here is afraid of the dark as well, and it's noisy to boot. So this one here is actually has two problems. So I'll remove both of these. So now these are the indicator ones. Here, I'll just turn this back on. These are the indicators. You can see they're kind of a darkened bulb that I pulled out of the front of these units. They're marked DS1 on the schematic as the indicator. Let me plug these things in and see what happens. Nothing. So I'll plug this one in. Hey, that one lights. So let me turn the current up. Crank the current up here. Just give it max current because you can see it's really low. So let me turn this one around and see if it strikes. Actually, me just bringing my hand close to it is almost making it try to strike. See that? So I'll move this around. Let me turn it the other way and see what happens. You can see that polarization effect. It works one way, but it doesn't work the other. So these ones have somewhat self-polarized. And we get the correct waveform, but the amplitude is really low. So remember, this larger pulse should be right at the top, So if I cover this one up, let me turn the lights out here again. Kind of a dim looking orange neon. Put this on top. That's not afraid of the dark. That one's okay. Let me cover this one right up. No problems. They operate just fine in the dark. It's just that they need more current. So one could actually modify the circuit to give them a little bit more current, and these might actually be okay. Now, they may have done this purposely. They may have used a different neon in the front so you couldn't take that out and swap it in. Maybe a neon that would operate like this. Who knows, right? I really don't know. But they are working. That is the correct waveform, and we can check that. So when we look at this, we should have a 160 hertz or so pulse, and that should look different. You can see that. There we go. Right? 165 here. Yep. 165, no problems, right? It is working. The current is low, so it's probably shifted the frequency just a little bit. So, turn the light back on here. Remove these. So those are the two indicators there. Now I have a whole bunch of NE2s here. These are the NE2s, and some people say that NE2s are relatively reliable. Now, I've tested a whole bunch of NE2s, and I find that only very few of them actually do anything. They're nice and bright. Another thing I found is that these neons with a very short bulb are the ones that work the best. The ones with a longer bulb and the longer electrodes don't work as well. Look at that. That's nice and bright. That's a nice orange neon bulb right there. Let's plug another one in here and see what happens. Probably need to turn the current down. This current's turned right up. So I'll turn the current down. As you can see, we're still getting that incorrect waveform, and that's at the lowest amount of current right there. So let's try turning one of these around just to see if we can make any differences here. Nope. Let's try this one over here. Now you got to remember, again, threading a needle at a distance, right? That's looking like it's trying. Let's see what happens when we adjust the current here. Nope. Maybe if I was to reduce the current, it might actually operate. So you can see these are the NE2s. I'll just try these in different sockets and see how that works. Pull this one out. Try this one. No. Turn it around. Try this one. No. Looks like it's almost there. Looked like it was almost there as I was touching it. It's trying, you know. Trying to get that kind of a staggered waveform, but it's just not doing it. Move this one out of here. Try this one here. And as you can see, no good. So these are all NE2s. So I can grab some more out of this bag here, pull these ones out, put them down here. Just grab a couple out of here, just for the sake of trying them. So with one of them, you get a really nice looking waveform, but it's not the correct one, and it wouldn't work. Look at that. Almost have a success here with these two. So let's see what happens if I give it a bit more current. Oh, you can see it pops. It pops out. So I'll just try turning these around, see what happens. So I'll take this one out and turn it around. Well, it seems to be that. So let's try this one here. Turn this one around. Same kind of thing. So it looks like we kind of have success here. So maybe I'll try one of these. Move this one out of the way and try and pair this with this one here. Same kind of result. So it's kind of telling me that maybe this one here is the one that's trying to initiate the correct pulse. Nope, that one doesn't like it at all. And this one here. So let's move this one over to this side and try this one on this side. So these are the two that I originally tried that almost gave us the correct pulse. Nope. Turn that one around. Nope.
So you can see we almost get what we need with these two, but they have to be in their appropriate sockets. Very, very picky. So it's almost there with those two neons. So let's just try, for the sake of it, just another random neon. Nope. Seems like this one here is the one that's trying to initiate it to make it correct. But there we go. Look at that. We have this with two of these neons right here, somewhat. Oh, and it's getting grouchy. So let's see what happens. If I turn the current up. So if I turn the current down and get it to a certain point, it almost looks like it wants to start. But not quite. It's almost like if I could turn the current down just a little bit more, I might be able to get rid of that, and it might actually try to work. Now, I'm sure we're going to see this if we optically look at this. So let's find out. Look at that. Even though, right, you can see that it's just not happening. So when we look at this optically, that's the type of pulse we're getting. So that would definitely not work in the chopper block. So that could even be, construed as, oh, hey, it's just kind of working. But as you can see, we have pretty much, well, close to the same frequency on the bottom. And then look at that pulse. So we have 161 here, and then we have a compromise both in that one. So the meter would not work correctly with that. So you can see how incredibly finicky this is with neon bulbs, and that's just a few, and you've seen how many I've played with and tested, and it's just like that. So what I'll do, actually, is I'll go grab a set that are matched, which are right over here, I believe. Click on the lab lights for a second. See what's going on. So these two look like they're matched right here. So I'll grab these and pop these in. So this one has got the mark on the top and on the bottom, which means it's the bottom. And I'm not sure on which side is going to be the cathode, so I'll put that in there. Looks like it tried to start. And I'll put this one in here like so. And there we have it. So you can see, a lot of experimentation brings that about. And then if I cover this one, now this is kind of loose in here, hopefully it keeps making connection. See, that one's not making connection all the time. Let me see if I can. I think this is one that I actually salvaged out of a nightlight. This one right here. Just to test it. And it seemed to work okay. I was very surprised. So I'll just put this over this one and see if it still oscillates. As you can see, in the dark, no problems. And I'll cover this one up, put it in the complete darkness. And no problems. So this is a set that would work. So I'll adjust the current up, see if it changes. So turn it up, down. Too much current causes a problem. So that's way over current right there anyway. So I can bring this way down to here. That's where it's supposed to be. And it runs no problems. Runs just fine. So this could be used, and this would run successfully in there. Now, they're not optimized. Again, one's out of a night light, and the other one is one of the ones out of my batch. But it gives a waveform, and it's stable. Seems to work okay. So this would, work in there. So you can see how incredibly picky this thing is, and that's why I ended up designing a solid-state version. Let's take a look at that. This is the solid-state chopper board that I've designed, and it turned out very, very well. This is the schematic for this board, just some of my scribbles. Now, this is very close, but I did change a few things, and that has to do with this network here and this network right here. On the schematic, I have two variable resistors, one in the frequency network and one in the duty cycle network. So I can adjust the duty cycle and I can adjust the frequency, so kind of trim things up. I found that I wanted to save space in here because I need to have those felt tabs press against this area here, so I didn't want anything in this area. So just by hand selecting components and basically grading components and installing them, I could get a result without having to install 3mm by 3mm square variable resistors on this board. Now they're pretty shallow, you know, they're not much higher than the surface mount IC, but still they're going to come pretty close to that wall, you know, when the board is in there, because you have the thickness of the board and it only will go in so far, right? So I just opted to stay away from that. So with the ICs and the components here, there is actually still quite a bit of clearance, so I don't have to worry about anything shorting out or anything like that. So I just opted to go with surface mount components and just hand grade them until I get to a center value. Now this board here is tuned to about 165 Hertz, so the range for this, what they specify, is about 160 to 170. I'm all about center values, so this one is tuned to 165. And that has to do with this little network right here. So this is replaced from this point, pin 6 to ground. It's replaced with a 200K resistor. And the capacitor here that's on pin 5 is also hand selected. So to give you an example, if you get a roll of surface mount 0402 parts, which is what this is using, and there's a bunch of, you know, 0.022 microfarad capacitors, it seems like they're pretty accurate, but actually they're not. So, and you know, either are the resistors. So the resistors move around just a little bit, and a combination of a value of a capacitor that's off a bit and a resistor that's off a bit will be the result from, say, 155 Hertz will be a combination, and it'll change one capacitor and it'll go to 160. I'll put another capacitor in, it'll be 162. Put another capacitor in, I'm backing down into the 150s again, and then I find one capacitor that puts it right at 165. So there's the golden component, right? So then when I find the rating of the capacitor that puts it right at 165, I measure it, and then I just grade the other ones to match. And same thing with the resistor, so I know I have a matched set. Now, I spent a little bit of time with that, not a whole lot of time, and you know, it turned out to be a nice center value, so I don't have to put that VR on there. And it was the same with the duty cycle network right here. So this programs the duty cycle of this IC. So this gives me a positive 25% duty cycle, and you'll see that on the scope here shortly. I'll show you what I mean. So I just select any 82K and any 22K resistor and put them in here, and in this form right here without the VR, but put them in here like you see. And then I use a fixed value and I just change this. So I'll try 3.4K, 3.6K, 3.8K. And then when I find the value that, you know, gives me 25% positive duty cycle and around 75% negative, I'll just use that component. So they're fixed. So this is basically a tuned board. So hand-picked components on here. And it works out very well that way. Again, I don't have to have variable resistors in any adjustment. And this is my spare board, right? So if I want to use this in one of the devices, I just have to put a positive and negative on this point, and away I go. Now, the LEDs on this that you see right now are on the wrong side of the board. This is just for experimentation. The LEDs go on this side of the board, and this will get spray painted flat black or satin black like you've seen with the other boards to stop any light reflection. And the LEDs themselves, you can see that I've sanded them. This is very important. Sanding them so that you get more of a uniform light, because it's kind of focal with these LEDs. These are super bright LEDs. What I'll do is I'll zoom on into this and I'll show you the board here and get us about as close as I can with this lens. So that's the board right there. So first of all, I got the LED here, so let's take a look at that. So on the bottom, you can see there's kind of a gold paint. Now that's just a pen that I had around, and that's very solid paint. So when I take the pen and dab that on the bottom of the LED, no light will shine through that. It's almost like, you know, putting a very thick black paint on the bottom. So this gold works very well. No light comes through that at all. So that's the reason I've done that. And then of course, as you can see, I've just sanded this with some 800 grit sandpaper and, you know, worked around it to make sure that it's all uniform. And that makes a very nice light inside there. Now, again, when I install these on the board, this would be on this side of the board. And it's nice that they have these little crimps here, so they'll only go down so far on the board. I don't know if you can actually see those little crimps, but there are little crimps on there. Kind of you can see they're kind of rectangles on the leads right there. So when you put this down onto the board, they stop at that, and it's the perfect height.
Nothing needs to be adjusted. So they sit square, nice and perfect right on the board, and they fit right into the block. So you can push them too far into the block, or you can bring them out too far. And it just worked out that it is the absolute perfect length. And I'll show you the one in the actual photo chopper block here in just a little bit. So the components on here are 0402 components, resistors and capacitors. You'll notice on here I have a bunch of parallel 10K resistors, and the reason I've done that is I just gave myself a lot of room for experimentation. Lots of different surface mount components will fit on these pads, and this was the experimental board, so lots of them got put on here and removed. I can't tell you how many times I've put parts on here and removed them, and you know, the board holds up very well. This board is just made right here. I make all my boards right here at Mr. Carlson's lab. So, and on Patreon, all the boards that I show everybody how to build are, you know, designed right here and, you know, released up there like that as well. So all the plans for the circuit boards are released on Patreon. But anyway, so these resistors here are the very first values I tried, and these are 1K ohm. Okay, so these are 1K ohm in parallel, so I get 500 ohms to this, and these were, you know, because these are super bright LEDs, these are very bright. They're so bright that they shine through those glass beads on the photocells onto the wall of the Hewlett Packard and kind of interfere with each other. That's how bright it is. So I really had to tone that down. So this went from 500 ohms to 5K ohms. So you'll see here on the network, there's 10K and 10K now, and they're in parallel. The only reason I'm using two 10K resistors is because I have pads and I don't want them empty. So I just put two 10K resistors, and it turned out when I looked at the photocell with the oscilloscope and I lit them with the LEDs, so I put the LED board into the photo chopper, and then I removed this and then put the neon board in the photo chopper, the amplitude is near identical. So if you were to just say, okay, guess which board I've put in, put, you know, the LED board in, take it out and put the neon board and say which one was which, you wouldn't be able to tell the difference. The waveform that's coming out of the photocell with the LEDs to the neons is near identical. So it worked out very well. And that's with the sanded LEDs, them sitting at the right height, the board blackened, and of course, you know, the paint on the bottom here, and 10K of resistance. So you could safely say if I was to redesign the board, I wouldn't do it with these two resistors now. I know that I could get away with, say, 4.7K would be fine. It would be within the range of brightness. So it'd be 4.7K right here, and that would just be a single value, right? Because this is 5K now because they're in parallel. So 4.7K here and 4.7K here would just work out very well. So that is that. So this is tuned at a center value, 165 Hertz. That's where this one is operating right now. The IC itself is a TL494C. That's the little surface mount component there. And these are just some noise reduction capacitors right here. So 2.2 microfarad capacitors that sit in there. And with the board in the block, there's still a lot of space to the actual wall. Again, this sits against the block, so this goes into the block, and then the wall would be on this side, right? So the little felt pads press against the board right here, and then of course there's a rubber grommet on the wall where the wires run in, and that presses against the board here, which you'll see in just a little bit when I take the actual photo chopper block out of the Hewlett Packard and show you this here. So I'll just move it over and I'll show you the board. I'll show you what the solid state photo chopper board looks like in this photo chopper block. So in order to get at that, I need to remove the screws on the side. So when I'm working on this, I usually only put 2 screws in the side. And when I'm testing it out, I just do that to keep every bit of light out of the case. So as you can see, there's lots of holes in the case here where light can leak in. So this is the rubber grommet, and this is where the cable runs in. This runs over into the back side here, and it's just soldered down there to those battery pins right there. So these still come off. It's just soldered directly to the board. And it's not a very pretty soldering job right now because this has been out of here many times. So this, at this point, is pretty finalized. These are those screws I was telling you about that work very well. They have somewhat of a coarse thread on them, and they fit right into that block and tighten it up beautifully without bottoming out on the photo cells. So I'll just put this up this way right here, and I'll take this out like this so the photo chopper block doesn't fall. There it is.
And let's push this over and zoom on in, hold that in place. Okay, so let's remove this away from the wall like so. And that is the chopper block right there. As you can see, it has some mileage on it. So somebody's been in here a lot. And there are those LEDs right there. As you can see, they're sanded and they're right at the right level. And then you can see the little felt pads there, just to make sure that everything is perfectly spaced. Now the rubber grommet does that comfortably on its own, but that's just there for a little bit of added protection. And I'll just poke this through like so. And you can see the back side of the board. Same thing as this board right here, right? Exact same thing. It's just that this is painted. And that's that. And that just sits against these little felt pads. And then the LEDs go into these two holes, just like so. You can see the bottom one going into the hole there. And it's just at the right height, as I say, with those little rectangles that they've punched into the legs here. It puts the LED right at the perfect midpoint of the photocell. So that worked out really nice. And then this just goes back together like so, and then tightens up against the wall. Just put the screws in and away it goes. So that worked out very, very well. It fits just like so. So I can feel the tension. You can see how it holds it away. That's the rubber grommet actually that's pushing this away. So there's a lot of tension on that board. So nothing would ever short or anything like that. I don't know if you can see down on the bottom there. That is the original mercury battery holder for the Null. And that piece of high heat pipe that you see down there, I'll just use something to point. Piece of high heat pipe right down here in the bottom, right in there, is where the two button cells are. There's actually two button cells right in that little piece of pipe down there. So it just sits in this holder. It's not in the holder at all. Of course, those batteries are no longer available. So that's just holding the new silver oxide button cells for the Null setting. And as you can see, the boards are recapped. You can see all the brand new electrolytic caps in there. Right there and there, all over the board. That worked out very, very well. So what I'm going to do is put the photo chopper block, that's right here, back together again. And I'll bring this into lab number 2, and I'll let this be powered up for a while, so basically stabilize. I wouldn't really say warm up because there's nothing in here to really get warm, but just let everything stabilize, turn the power on, let it sit for a while. They suggest that in the manual as well. And then I'll attach this to a calibration device, and we'll see how close this is down on the 3 microvolt scale. We'll see how incredibly close this meter comes in. See how accurate this thing really is. So that should be a lot of fun. That's coming up next. I forgot to show you the battery pack that I put together for this thing. So basically just like a microphone connector in the bottom here. And just open this up. This thing hasn't been charged through this entire process. Pretty amazing. That thing really is a current miser. There it is. That's the entire battery pack inside there. So this here just comes out. There's, as you can see, everything has a felt spacer to hold everything nice and centered in here, and this is pressed just comfortably tight. There's 20 AA batteries in here, so there's 20 Eneloop batteries inside this pack here, which gives me, about positive 13 and negative 13 volts. There's 2 fuses just in case anything goes wrong on the outside, just in case anything shorts the pins. I wouldn't want anything to go wrong. So these are they're absolute value fuses. These will only go if something really bad happens. So they're 5 amps each. And little standoffs in here. You've seen me use these standoffs in a lot of the vacuum tube repairs that I do. Standoffs just holding the wires, and then that holds the fuses right to the pins here. And that's really it. This will come out like so. Show you in there. That's what the battery pack looks like. It just fits into that nice little felt cradle on the bottom. Like that. And that's it. Very nice battery pack. Works very well. Again, still working on its original charge. The charge that came with the batteries. So I'm very impressed by that. Quite a simple build. Worked out well.
just for the fun of it, let's check the accuracy of this Hewlett Packard 419A on the 3 microvolt scale. Now keep in mind, no final alignment or anything has been done yet, and the boards have been out of this thing a lot of times. I've recapped them. Can't even count how many times I've had that photo chopper apart, working with the neon boards, and then of course now it has the solid state board in there. So in order to check the calibration on this, we're going to use this Fluke 5440B. Right now I have it set to 3 microvolts, so we're ready to go at this point. So in order for me to turn this on, all I have to do is just press that button. I also have the divider on right now. And the cables I'm using is just a piece of coax and some banana plug adapters. That's all I'm using. And we're going to check the accuracy with that. So, again, in order to be nice to this meter, I haven't done any finalizations on any type of alignments or anything. I've had the boards out of there so many times it's not funny. So if it reads way off, be nice to it. So I've set the null already. The null seems to be pretty close still. It's always a good idea with these meters to press the null button in and let them sit for a while so the battery voltage can settle off. So as you know, when you disconnect a load from a battery for any period of time, the voltage will climb. And then when you apply a load to it, the voltage will come down and then usually settle off. And that's what's happening with this right now. So I've had that null button pushed in for quite a while. So I'll just zoom on into that portion of the meter right now. So zoom right into where the 3 is. Okay, HP, be nice to me. Here we go. I'm going to turn on the calibrator now. So we'll probably see the needle take off for a moment. And let's see what happens. Here we go. Now keep in mind, no alignment. Look at that, it's right on top of the 3. That's incredible. Do you think I should be buying a lottery ticket at this point? Okay, so I shut the calibrator off again. I'll recheck the 0. For the fun of it, let's check it at 1 microvolt. Hey, we've gone this far, and it looks like it's that crazy accurate, so why not at 1? Let's move this over just a little bit. Should be right in front of this. I'm just going to move the entire camera over just a hair to get this right in front of that 1 so that we can really see how close this is going to get. So now keep in mind the needle, a little bit of movement in the needle is basically due to temperature variation and everything else in here right now. That little bit of movement to the first increment on each side of the 0 is 100 nanovolts. So even me moving my hand close to the meter, me turning the camera on and off, things like that, that will all affect this. It's that incredibly sensitive. I should have probably grounded out the tripod of the camera as well, but this is just, we're just having fun right now, right? Okay, it's pretty close. Right, we're just under the 0 mark. I just want it to settle off. There we go. Not too bad. I might just touch it up just a hair. Looks like it's just hanging out on the low side just a little bit. Again, temperature variation, that's pretty close. So I'll turn on the calibrator now. I'll just turn this down to 1 microvolt, and I'll turn this on. Is that not incredible? That is incredible. 1 microvolt. Wow. Okay, I'll shut this off. I'm going to be really crazy, and let's just check this at 500 nanovolts. We're almost in the noise right now. Keep in mind, this is just a piece of coax and some conversions to banana plugs here. And that's plugged into the front of the calibrator, right? Okay, so we're pretty close to 0. Just want to make sure that it is, because any kind of movement right now is, we're just dealing with noise. So, okay, so I'm going to adjust the Fluke to 500 nanovolts. So that would be 500 nanovolts. Just check this again. I'm moving around here, right?
So me just moving around will affect this. So I'm going to just move my hand there. Okay, here we go. Okay, are we going to get 500 nanovolts? So that's right between the 0 and the 1 there. Come on, HP, you can do it. So right now we're sitting at about 450, and it's just about to touch 5. So we're between 400 and 500 nanovolts right now. Not bad. Okay, so what I'm going to do is just recheck the 0, and we'll try this one more time just to be absolutely fair, because it's been so accurate on all the other ones. See, it's right around the 0 there. It's hanging out on the low side, and that could be that, 50 nanovolts that were out. So I'm just going to touch the null up, very carefully move in here, and just tap on the null. Okay, so let's see if that's going to settle off. I want to be as fair as possible. I want this to average the 0. That's what I'm doing. Alright, I'll just touch this up just a little more. That was me moving my hand in towards it. You can see how it just came up. I'll move my hand away. Okay, I'll just touch the 0 up. It's me moving my hand in again. Move my hand away. Okay, so here we go. 500 nanovolts. Let's see. On. Look at that. Isn't that incredible? No alignment. What is the deal here? That's averaging the 500. Keep in mind each side is just noise, right? There we go. Do I even need to align this thing? So let's just check the 10 microvolt scale while we're here. Let's have some fun. Turn the calibrator over to 10 microvolts. Move the digits over. So there's 10 there. So what I'm going to do is I'm going to move this up to the 10. So I'll show you what I'm doing here. So I'll move this up to 10, and I'm going to have to readjust the null again. Which is absolutely fine. Move the null. And let's just let that sit for one moment just to see if it's going to settle off. Zoom on into the meter here again. So now we're on the upper scale right here, not the lower one anymore. I'll just let this settle around the 0, and I'll just touch it up here in a moment if it needs to be touched up. Okay, so I'll just touch the null up just a hair. I want this to be as fair as possible to this meter, so just let this average out for a moment, right? Again, 10 microvolts is pretty sensitive scale. Okay, that's close to the 0, right? Let's try it and see how close it comes to the 10 at the end. Here we go. Look at that. That is just crazy. I'll move the camera over just to make sure that we're straight on that. Look at that. What do you think? Do I even need to align this thing? That's just incredible. All I have to say is I'm extremely impressed with this thing. For the amount of time that this thing has been, I'll just back the lens in here, for the amount of time that this thing has been apart, and I've had to face off this, boards out, recapped it, everything. You know, you'd think that maybe I would have bumped those VRs just a little bit or something, but it's spot on. What do I say? It's pretty incredible, and it'll read all the way up to 1,000 volts as well. You can even test it on that scale if we want, but if it's going to read this accurate down here, I'm pretty sure it's going to be just fine. I'm very impressed by this device. So again, hats off to the designers who put this thing together. Like, I mean, that's incredible. It really is. There's no other words for it.
I hope you enjoyed this video involving the photo chopper. If you are enjoying my videos, you can let me know by giving me a big thumbs up and hang around. There'll be more videos like this coming in the near future. We'll be taking a look at vacuum tube and solid state electronic devices alike. So if you haven't subscribed, now would be a good time to do that as well. If you want to be notified as soon as I post a new video, don't forget to tap the bell symbol. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way, and gaining access to many of my electronic inventions and designs, you're definitely going to want to check out my ongoing electronics course on Patreon. I'll pin the link right at the top of the comments section, and I'll also put the link just under the video's description under the Show More tab. So if you click on the link, it'll take you right there and you can check it out. All right, until next time, take care. Bye for now.